Now, the question we've been dying to know since the last video. Can we factor this any further? Can we not? The answer is no. I'm sorry, it's anticlimactic, but that's the truth. That's it. Can't factor that any further. But what I was trying to say and hint at is our next topic. Complex trinomials. Yep. So, let's take a little while to trial and error box method. Firstly, how do you identify a complex trinomial before we get to any of that fancy stuff? So let's compare with a simple trinomial. So you see it's x squared plus bx plus c, that's the form, and the addition of a coefficient on the first term makes a difference. So here are some examples of some complex trinomials. They're not the most complex, but they're still complex, so whatever. How do we use trial and error? It's similar to the simple trinomial method of finding the sum of the middle term and the products of the last term, except this time we have to find two products because we have a coefficient in the first one. So here we have an example of a complex trinomial, 12x squared plus 7x minus 5x. So we have the products on either side, and we're going to use our magic buddy, Mr. Mike, in the middle to determine what the sum is going to look like. So we're going to make a box, because that's the box method, duh. Then we're going to put our choices of products in and use our up product and down product, which is just multiplying diagonally to get those two products to equal the magic middle term. So this is where the trial and error comes into play, because there are multiples of 12 and multiples of 5, and you got to just experiment until you get back to that 7 and negative 5. Whatever you got in that box, you want to just put a bracket around it, so it'd be x plus 1 and 12x minus 5, just like how it was positioned in the box. You're just going to FOIL it, check if it's the same, and then you're Gucci.
Let's say we have this equation. What makes it a complex trinomial is because the first number here is a 5, not a 1. So now when you do your box method, you have to figure out a number that equals to 5, which would be 1 times 5x. Now we have to figure out a number that multiplies to 27 but also adds or subtracts to 30. Now there's two numbers, which would be 1 times 27 and 3 times 9. Neither of these numbers, when you put a subtract or an add sign to them, equal to negative 30. Let's say we did 3 times 9. So you do 1 times 9, which is 9x, and you do 5 times 3, which is 15x. Even if you put both negative signs there, it still doesn't equal to 30. Now let's say we try 1 and 27. It still equals to 27 and 1. Even if you put a negative and a negative sign, it still doesn't equal to negative 30, making this problem not factorable. This is because no numbers, when multiplied, equal to the numbers in this equation. Okay, let's try a second example. Now for this equation, because the numbers are so large, we have to find a GCF. Which means you have to find the lowest number that fits into every single one of these numbers. And this can include one of these numbers, and it can include a variable. Now for the variable, you have to find one that goes into every equation, which would be the d. To factor this, we would divide everything in the equation by 9d2. If you divide everything in the equation by 9d to the power of 2, okay, this is what you would get after dividing everything. Now, this is as far as you can go while factoring. Another example that I'm going to show would be x to the power of 2 plus 8x plus 15. Now, we know that the box method can be used to determine this, and you know that 3 and 5, and this goes to 5x, and this one gets made to be 3x positive plus 5. One way to check your answer in this equation is by doing FOIL again. to see if the answers are the same as what you got in the original question, which would be x times x, x to the power of 2, x times 5 plus 5x plus 3x plus 15. Add those together to get this, what we started out with.